So we're finishing up this section, just graphs. Again, reminder, the single biggest and most important thing of this section is not even this section. It's, do you remember function transformations? If you don't remember function transformation, this section is going to be really hard. Okay. It's probably going to be a medium class lane. We're not going to go the full duration, but we got some good chunks to go through. So remember your function transformations, and don't be afraid to review 3.5 was function transformations, or was it 3.7? It was something in chapter 3. Example 2, write an equation for the following and find the domain and range. All right. So, no problem. Remember, by the way, this is going to be good. The domain and range of an untransformed exponential function, so something like e to the x or 2 to the x or something like that, is all real numbers and 0 to infinity, respectively. And remember that function transformations affect these. So if we move something up, well, then it's not 0 to infinity anymore. It may be 5 to infinity, right? If we move it down, maybe it's -5 to infinity. If we reflect it upside down, reflect it about the x-axis, maybe it'll be -infinity to 0. So if you remember the domain and range, and then there's function transformations, you can actually also use the function transformations on the domain and range. So anyway, part A is going to be f of x equals e to the x. Remember, e is Euler's number, 2.7182 dot, 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 dot. And we're transforming that. Vertical stretch by 2. Reflect about the y-axis, so left to right, and up 4. So we just have to do all this stuff. What does a vertical stretch look like? We need an equation. What happens with the vertical stretch? Somebody tell me, what do we get vertical stretch by 2? Or any of these. How do we do any of these transformations to this function, e to the x? So plus 2 would shift it up 2. It's multiplied by 2 to vertically stretch it. But that's the right idea. So we have a 2 in the front. If it was a horizontal thing, it'd be on the inside, up here in the exponent. Plus 4, good, good, good. And then there's one more thing. What do we do with that reflection about the y-axis? Gets flipped left to right. It's a horizontal flippage. You may have been wrong, but at least you answered, which is always good. So you get a good Lexi from me. It's a negative, yes. And specifically, where is the negative? Negative here does something, negative here does something. Question is, which one? Which place does it go? Inside the function in the exponent, or outside of the function by the 2? I'm glad you answered the question, but similar to Lexi, it should be on the inside. Because outside is vertical stuff. So outside would flip it upside down about the x-axis. We're flipping it about the y-axis. This is a horizontal change, left to right. Okay, so it'll be on the inside. All right, and we need the domain, and we need the range. Someone give me either the domain or the range. The domain should be easy. By now you should say, Jason, why are you even asking about the domain? I could find the domain of an exponential function in my sleep because it's always the same. Any exponential function is the same domain. Will someone give me either the domain or the range? And then we'll move on to part B after that. Part B is going to be a transformation of 2 to the x. Nobody? Yeah, good, Lane. Good. Domain is all real numbers, right? Every exponential function, we can plug in anything we want. Negative infinity to infinity. Good. No, getting questions wrong is like half of the fun in math. It's good to get things wrong. All right, and the range is trickier here, right? There's a lot going on. We can look at the function transformations for range, right? So, you know what you should do? Just make a separate Twitch account that's called, like, I don't know, lover of rocks or whatever. So nobody even knows who you are. And then you can answer wrong all you want. And nobody will judge you. You could be anonymous. Who knows? I don't even know that Lexi Chenoweth is Lexi. What if y'all are pulling a fast one on me and you just switched your Twitch accounts? And then every time Lexi says something, it's actually Delaney, and I'm just getting super confused. Okay, so the range, right? The range of a standard exponential function, 0 to infinity. So we can use function transformations on this if you want. Or you could graph it. A couple different ways of thinking about it. But look at the function transformations, right? The range of a standard exponential function, 0 to infinity. Lexi just has like 5 different accounts. She's the only one watching the lecture. Everyone else is just sitting at home watching TV. If we vertically stretch this by 2, it multiplies all the y values by 2. 2 times 0 is still 0. 2 times infinity is still 0. Vertical stretching does not affect the range. Right? It just multiplies these y values by 2. Reflect about the y-axis, that's a horizontal change. Horizontal changes do not affect y values. Does not affect the range. Up 4, that is a vertical change. Up 4 affects the y's. Let's move all this up 4. Range is 4 to infinity. Good, Jason. I have to compliment myself. All right, and those are our answers. Any questions? All right, then let's do part B. Oh yeah, sorry, I'm not actually Jason, I'm Lexi. Well, I don't know. Part B, we have a transformation of 2 to the x. Okay, and this time I'm going to give you a graph. Okay, and you have to interpret the graph and see if you can figure out what the equation is. So these ones are tricky. These are important too. Okay? So I'm going to give you this graph, and you have to find the equation. So there's an asymptote at y equals -3. There's a point right here at 0, 2, and 1, 1, and then 2, -4. And it kind of drops down really fast, and then it kind of approaches this nice little asymptote, like so. And this is the problem given to you. How do we find an equation for this? We have to identify the function transformations first, and then find an equation and hope that's it. Okay. So there's some function transformations. Specifically, this is an upside down exponential function, right? Exponential functions grow. They get big. This one's dying off. This one's fallen to oblivion. This person fell off a half dome. They weren't like using the cables correctly or something. Don't be stupid if you hike Half Dome, by the way. It's a really nice hike. Kind of tiring though. Anybody going to Yosemite ever? Would recommend. So it's fallen down. So we know that there's some sort of vertical reflection. All right. Vertical is x-axis. Right? It's flipped over this axis, upside down. There's something else that we know, is that usually exponential functions, right? Usually exponential functions have asymptotes at 0. This exponential function has gotten moved up 3 units. Because the asymptote got moved up. Okay? After those, it's kind of hard to figure out if they're stretching. It's kind of hard sometimes for exponential functions to figure out horizontal shifts. So what I recommend is just trying this easier stuff first. Not easy, but not the harder stuff. This stuff is hard to find. Let's make an equation and then just check our answer. Okay? Well, Gabe, if you don't even know who you are yourself, that's really, really bad. Okay. Or sorry, apparently you're Lexing. So let's incorporate the information here, right? So it's 2 to the x with some changes. Reflection about the x-axis, that's upside down. It's going to be a vertical change. Vertical change means outside. Up 3, that's going to be a +3 on the outside. So I think this is the right answer. But we need to check our answer. Right? So you can just check our answer by plugging in x's and y's and see that we have the right points, right? So if x is 0, we get -2 to the 0th power +3. That's -1 + 3 should be 2. 0, 2 is on the graph. So that checks out. Good, Stella. Let's check this point. When x is 1, we get -2 to the 1st power +3. That's -2 + 1, which is +1. 1, 1. Good. Since we have both of these points on the graph, we know this is our answer. So all that's left is the domain and range. Okay. So the domain should be the easy part, because the domain of every exponential function is the same, right? Domain is x's. X is everywhere. We have every single x possible. Domain is all real numbers. Range, well, the smallest that we can get for the y values is -infinity. The biggest we can get for the y values is 3. And it's a parenthesis because we never hit 3. Sometimes I get a little excited. I just start writing off the paper. Thank you for asking. So we found the function, found the domain, found the range, and it kind of looks like a robot dog head. Give him a little body, little robot body. Woof. Some puppy ears. All right, and that's the section. It's all of 6.2. Draw. It's a dangerous question. Dangerous request. Maybe after class we can turn this into an art class. But we've got to talk about the next section. Any questions on this one before we go into the next section? Because this is where this class really gets juicy. Okay? This is where this class turns from like a regular meal to a delicacy. We get into logarithms. Don't be scared. Don't be scared. This is good stuff. Okay? So remember when we were talking about compound interest, we were trying to solve an exponential equation and we couldn't do it, right? If we try to solve something like, I don't know, when is 3 equal to 2 to the x, right? 2 raised to the first power is 2. 2 raised to the second power is 4. But what power do we have to raise 2 to get 3? And we don't have a way to solve this yet, right? No way to solve yet. Because to undo multiplication, we divide. To undo addition, we subtract. To undo squares, we square root. But we're missing an inverse function. We have no inverse function for exponentials. So we need an inverse. We need to undo exponentials. And we talked about what that word means. That word means inverse. It's like 1.6. I don't know. Let's see. Let's look at it together. Right? When is 2 to the x equal to 3? Yeah. About 1.6. Good. This number, by the way, over here is log base 2 of 3. Log base 2, 3. 1.58492625, etc. An irrational number. So, let's talk about that. The inverse of 2 to the x is called log base 2 of x. Let's introduce logarithms officially. Okay? Definition. For log base b of x. That's how we say this. The definition of a logarithm is actually going to be kind of a weird definition. We will get to that, Lexi. Your calculator doesn't have log base 2. It has 2 logarithms, though, that we'll get to either later today or tomorrow. So log base 3 of 2 is not on your, or log base 2 of 3 is not on your calculator, but later on, we're going to introduce a nice little magic trick to show you how to calculate that. Okay? So log base b of x is equivalent to b to the y equals x. So one of the big things, and I kid you not, the next 15 minutes of class is going to be the most important 15 minutes for the next week of class. Okay? As we talk about what this means, if you get this, when we do examples talking about this definition, you're not going to get the definition yet, right? We have to work through it. We're spending time talking about what this means. If you eventually get what this means, the end of class, the rest of the class is going to be way easier for you. If by tomorrow you still don't really get this, the end of class is going to be very, very difficult for you. Okay? But it's not as bad as what it looks like. So essentially what we have is we have things called this is what's called the logarithmic form. And it has an equivalent exponential form. So I know I made it sound really bad, but it's not going to be that bad. So anytime you have a logarithm, this is big. If you don't like logarithms, this is important. Anytime you have a logarithm, you just use this definition and say, no more logarithm. You can make every logarithm just go away with this one simple trick. It's my clickbait title. Okay? So notice what's the difference between exponential and logarithmic form. So we say that b is the base of the logarithm. So notice the base, bottom, it's on the bottom of the logarithm, a subscript. It's also the base of the exponential. It's on the bottom of the exponential function. We're going to do them by hand first, because if you can do them by hand, some things by hand, some things you can't. If you can do some of the problems by hand, it's going to make the future sections way easier, but you do not have to. Eventually, you will be able to use your calculator for everything. But I recommend that you do it by hand, because if you can learn to do them by hand, the future sections are going to get way easier, because future sections are going to have a bunch of variables and stuff, and we're not going to be able to use calculators for those. So the base of the logarithm is the base of the exponential. Okay? And the output for a logarithm is the input of the exponential, kind of. So let's just look at this. Let's look at this, okay? Example 1. Write an exponential form. Part A. Log base 6 of the square root of 6 equals 1/2. So this is a silly equation, because this is just a true statement, right? We're not solving any problems right now. We're not doing voodoo magic. This is a true statement. We're going to write this true statement in a different form. Say that hypothetically you do not like logarithms. Then we can write it in exponential form and not have to worry about logarithms at all. Okay, so how do we do that? We look at the definition. Okay, log base b. b is 6. This is our base. And this is our y from the definition. It's equivalent to the base raised to the y equals the input. So this is the same as the base, which is 6, raised to the y, which is 1/2, equals the input, square root of 6. These are equivalent statements. And this thing over here is the exponential form that we were asked. So these are both true, right? 6 to the 1/2. Remember, rational exponents. 6 to the 1/2 is the square root of 6. And this thing should be true too, right? If you type that in, I type that in, right? Log base 6 of the square root of 6. Well, if I type that into a calculator and not Google, it'd pop up, right? It will always be a true statement. But that's a good question. If you're answering this question and you get something like 6 squared equals 5, you done goofed, okay? So you shouldn't see something like this. You should always see a true statement. All right. So let's do another one. Part B. Log base 3 of 9 equals 2. This is a true statement. Eventually, when we talk about how to evaluate logs, you'll say, okay, that left-hand side is 2. So 2 equals 2, that's right. But we are not evaluating anything yet. We're not doing anything. We're just changing the form, right? We're looking at the little spray bottle one way, and then we're looking at it the other way. It's still a spray bottle. It's still an effective deterrent for cats. Although not that effective. October. That cat. Okay. So the base of the logarithm is 3. The y value is the output. So in exponential form, it's the base to the y equals the x. So you just use this definition. Say, okay, base is 3. Y is the exponent. And that should equal the inside, which is 9. Is this a true statement? I sure hope so. 3 squared is 9. And this is the exponential form. Both of these are true. Just one's in logarithmic form and one's in exponential form. That's the relationship between logarithms and exponentials. All right. Oh, fun fact, by the way. Yesterday, when I was playing some League of Legends and streaming it, I used the intermediate value theorem to show people some things. It was pretty interesting. So you too might use the intermediate value theorem someday. All right, let's move on. Part C. Essentially, yeah, for this sort of stuff. So let's look at part C and see if you can get the answer. Okay. Part C, and let's have you guys see if you can do the answer. Part C is log base 5 of 25 equals to, what's the exponential form? Someone in the chat, give me the exponential form of this logarithmic equation. Five squared is 25. Beautiful. Perfect. Wonderful. Good. I kid you not. If you can answer this question, and of course, don't forget it for the rest of class, the rest of class is going to be way easier. Because this is just what a logarithm means. This is what logarithms mean. If you can remember that, the future will be easier. It's good work. Okay, now let's go backwards. I'm assuming Gabe's good with that paper, but if it's not, Gabe, you let me know. Okay, example 2. Write in exponential form. Part A. Wait, we just did that. Write in log form. Okay. Good, Lexi. Good. 2 cubed is equal to 8. So now we're just going to go the other direction. So this is a true statement. 100% true statement. 2 cubed is 8. We're going to write another true statement. Right? The base of the logarithm is the same as the base of the exponential, right? Base of the logarithm, base of the exponential. These are always the same number. So we're going to have log base b, it's still going to be the same base. And then what goes on the inside of the logarithm? What goes on the right-hand side? One of them is going to be a 3, one of them is going to be an 8. Which one goes where? Yeah, the 3 is going to be on the outside. Good. And the 8 is going to be on the inside. Excellent. Good stuff. So let's do 2 more of these. 5 cubed equals 125. And 10 to the negative 4th equals 1 over 10,000. So I want you to think about these, try to get the answer, and while you're thinking about them, we'll do the attendance question for day. I cannot believe I have not used this attendance question yet. The attendance question is, are you here today? It's taken this long for that to be the attendance question. But that will just be the question, are you here today? So send that to me in Discord. And then if you give me the answers here, I'll be happy. It's going to be a log somewhere. And there's going to be a base, an inside, and the right-hand side. All right. So what's the base of the exponential? It's 5. So we know it's going to be log base 5. And then the exponent's the right-hand side, and the right-hand side is the inside. Okay? The base of the exponential is 10. So that's going to be our base of our logarithm. And the exponent is the answer. All right, I kind of wrote it small, but that's the idea for these. So if you can do this, you can do basically this whole section, because this unlocks you to do things you didn't know were possible. Okay? No, small exaggeration maybe, right? So we can now evaluate logs by hand. And you might not believe me, but you can. All you have to do is this. And hopefully you remember your exponents. Okay? Laws of exponents are going to be big there. I didn't actually put B here. Evaluate. Eventually, I actually forgot. This is actually, in this book, we don't get into doing this with a calculator until 6.5. We're going to be doing it by hand until then. There's something called the change of base formula, though, that lets you type things into your calculator. But again, we'll talk about that more later. You can evaluate this. Y equals log base 4 of 64. And maybe you don't know the answer here. Maybe you don't know what log base 4 of 64 is, especially if you're just learning about logs for the first time today. But if you don't want to worry about logarithms, let's not use logarithms at all. Let's get rid of the logarithms. We have a logarithmic equation. If we could write this as an exponential equation, then we could answer this using what we know about exponents. Okay, so we do the same thing. Base of the logarithm, that's 4. So we get 4 to the y equals 64. And the question is, what exponent makes this true? Well, 4 to the first power is 4. 4 to the second power is 16. 4 cubed, you can type that onto a calculator or multiply this by 4, 64. So what's our answer going to be for part A? What's our answer? Essentially, we have to ask ourselves, 4 raised to what power is going to give us 64? And then what's the answer to that question? Yeah, it's 3. Good. Very good. Logarithms, no joke. Logarithms and function transformations are the hardest parts of this whole class. Logarithms and function transformations. If you can get logarithms down, you should be good to go. Okay, let's do another one. Part B. Log of 121. Log base 121 of 11. So what's our first step? The rhetorical question. I don't want to take too long. First step is, again, saying, well, I don't know what log base 121 of 11 is, so let's write it in a different form. Notice there's no y equals, but you can call it x, you can call it y, you can add this if you want. Right? And then, again, this is our base. 121 is the base. 121 raised to what exponent is going to be 11? Oh, yes. Gabriel Munoz, 307, is Delaney. Is Lexi. I forgot. My mistake. So this one's trickier. What's going on with this one? Does anybody have any ideas? Because if we did the same thing, right? 121 to the first power is 121. 121 squared is, I don't know, something really big. We need it to be 11. So what do we do? We have to remember how exponents work. We're going the wrong direction. Yeah, so square roots and negatives are going to be the hardest part of this section probably if you get the definition of a logarithm down. And 1/2 is the answer. Very good. But for those of you who are not Lane, sorry, I don't mean to put you on the spot. But for most of you, you might not see exactly where the 1/2 comes from. So remember that it is the square root. The square root of 121 is 11. So the question is, what exponent gives us a square root? Right? Right. A square root is an exponent of 1/2. Because 121 to the 1/2 power is the square root of 121, which does give us that 11. So you're going to have to remember how roots work. Square root is 1/2. Cubed root is 1/3. And you're also going to have to worry about negative exponents. Negative exponents are going to give us the fractions. And don't worry. That's part C. Okay, good stuff. Part C. Y equals log base 3 of 1/27th. So again, there's a lot going on here, but regardless of what's going on, we want to write this as an exponential equation. For most people, not everybody, for most people, if we write this as an exponential equation, it'll be a little easier. So again, we just say base of the logarithm's 3. That's going to be the base of our exponential. 3 to what power is 1/27th? So again, we're not just going to, 3 to the first power is 3. 3 squared is 9. 3 cubed is 27. That's close, right? But we need 1/27th. So the answer is not going to be 3. 1/3 is what it would be if it were flipped around. But 3 to the 1/3, we'd have to flip it around for 1/3 to be the answer. Because 3 to the 1/3 is actually the cubed root of 3, which is not useful. It's -3, yeah. Good, fake Lexi. Good. All right. Because notice that 3 to the -3rd power is 1/3 cubed, which is 1/27th, which is exactly what we wanted. Yeah, you're welcome, Lexi. You're welcome. I'm glad you appreciate it. Lexi has a lot of accounts. Lexi has a lot of accounts. Oh, good stuff. Good stuff. All right. Part D. Y equals log base 2 of 1/32. I'm very proud today. I'm very proud. All right, so this one, we do the same thing. Base of the exponential is 2, because that's the base of the logarithm. 2 to what power is 1/32nd? 2 to the first power is 2. Right? 2 squared is 4. 2 cubed is 8. 2 to the 4th is 16. 2 to the 5th is 32. That's close. So yeah, -5. Excellent. Nice. We really actually could finish this whole section today. Let's finish it. It's not going to take that much longer. Maybe 10, 20 minutes. Finish the section, which put us a little bit ahead, which means Friday we might be able to have a short day if we finish today. Okay, so let's go with this. So those are logarithms in a nutshell. If you have a calculator in front of you, though, you notice you don't have a log base 3. You don't have log base 2. On your calculator, you do have a log button, though, but there's no base. That's called the common logarithm, because some logarithms are so common that we use shorthand. Just like, right, we don't write the square root of 4. Right? We just write the square root of 4, but we don't write the 2, because the square roots are so common, we don't use the 2. If there's other stuff, we do 3, 4, and 5. That's the same exact thing as what's going on with the common logarithm. Okay? So just like square roots, we do a similar thing with logarithms. The common log is written without a base at all. And the common log is just log base 10. So if you don't see a base, we assume it's the common log, and you can put a 10 there. If you want to write a 10 there on all your stuff, you can. And your calculator has the common log on it. Okay. There's another one that we use all the time. And this one I really like. I really like natural logs because it's one less letter to write. We write that ln of x. Also, side note, notice how I'm writing my L's when I write logarithms. I'm not writing my L's like I normally do. I'm doing cursive L's. This is just something that I personally do so that this doesn't look like a 1. Okay. You already remember that my absolute values look like 1s. So that's just personally why I do this. You can write your logs with a cursive L. You can write your logs like this. It's up to you. But if you're wondering, that's what I do. And this is log base E. Again, Euler's number. ln. Your calculator has both ln and log. Almost every calculator does. Calculator on my phone does too. So, okay. That's what we have here. So we have 2 more example problems left, and we're just going to be done a little early today. Not only will we be done early today, we'll have covered more material than I expected. So should have a nice short Friday this week. Example 4. Evaluate. Okay, part A. Y equals log of 1,000. So again, if you want to, you can say common log, common log. Let's write a 10 here. Right? You could write y equals log base 10 of 1,000 if you wanted to. The important thing is that we convert it to exponential form. Okay? 10 to the y equals 1,000. And then we can just get our answer that way. Okay? The base of the logarithm, the bottom of the logarithm, the subscript, is the base or the bottom of the exponential when you're converting between these two forms. All right? Well, 10 to the first power is 10. 10 to the second power is 100. 10 to the third power is 1,000. So our answer is 3. And if you typed this into your calculator, you find the log button. If you can't find the log button on your calculator, send me a picture of it. I'll show you where it is. That's all we do here. Part B. Y equals the common log of 321. So again, this is 10 to what power equals 321? I don't know. Right? 10 squared is 100. 10 cubed is 1,000. So it's going to be between 2 and 3. But you can't just do this in your head unless you're some kind of math savant. So you use a calculator. Okay? and just approximate your answer. So you just type in log 321 on your calculator, and it'll give you that it's approximately 2.5065. Can't do this one by hand. Any questions on this stuff before we finish? 2 more parts and then the final example problem. Whoosh. And we are really chugging along today. But there's a lot of right answers in chat, so I feel pretty good about going at this speed. So we have y equals the natural log of e squared. So again, this one looks crazy. This one looks like you're riding the mechanical bull. But the mechanical bull is unplugged. Okay? Because what is this, right? What does the natural log mean? We look at our definitions. Natural log is just log base e. So how do we write this as an exponential equation? Well, the base of the log is e. E to the y equals the inside. So what's our answer for part C? Two. Yep. Perfect. By the way, you now are able to do half of 6.6. This is 6.3 right here. You can already do half of 6.6. We're kind of doing 6.6 early, solving exponential and logarithmic equations. Because this is an exponential equation. This is a logarithmic equation. All right? And this is some of the techniques that we're going to be doing later in the section. So again, if you're good on this section, it bodes really, really well for the future of chapter 6. And if you're not, don't worry, just ask questions, do the homework, send me messages on Discord. All right, part D. Y equals the natural log of 500. Again, we're going to have the same problem as part B. This is e to what power is 500? Who knows? Use your calculator. Use the ln button. Get ln of 500 is 6.2146. I'm glad you guys can keep track of who everyone is. I can't. All right, last example of the day. Example 5. So, the amount of energy released from an earthquake was 500 times the amount from another one. So this is going to be talking about magnitude. The magnitude of earthquakes. And the magnitude of earthquakes, like if you see like this earthquake had magnitude 6.2, this earthquake had magnitude 7.2. There's an interesting relationship with exponentials and the energy released. Okay? So this is modeled by the equation 10 to the x equals 500, where x is the difference in magnitude. Okay, and the question is find that difference in magnitude. So side note, a little bit of history on how magnitude works and like earthquakes. Really, this is kind of a simplification of the problem. Really, the situation that we have is 10 to the A equals 500 times 10 to the B. Don't pay attention to this. This is just an explanation. This is the energy from the first one. This is the energy of the second one. When we say magnitude of an earthquake, it's actually an exponent. So like magnitude 5 is like a 10 to the 5th in terms of energy. So magnitude 6 is actually 10 times as much energy as magnitude 5. Okay, it's sort of on a logarithmic scale. So if you're thinking of just how much energy is released from an earthquake, the difference in magnitude is a huge difference in energy. Okay, so again, magnitude 6, magnitude 7, that's 10 times as much energy released from that earthquake. Okay, but really all you need to do is solve this. So again, let's see. 10 squared is 100. 10 cubed is 1,000. So it's got to be some number between 2 and 3. We can't use exponents to solve this. I don't think so, but maybe. Is that a bad joke, Lane? Exponents aren't going to help us here. We need logarithms. So we need to write this, right? Can't use exponents here. We need it in log form. Okay? How do we write this in logarithmic form? Go back to the beginning of the section, right? Log form says the base of our logarithm is going to be the base of the exponential. This is going to be the common log, log base 10. You can write the 10 or not write the 10, as you prefer. And then the inside is that right-hand side, 500 equals x. This is what it looks like in logarithmic form. Despicable Me is so old. Isn't that movie like 10 years old or something at least? Hold on. 2010, yeah, 10 years old. You're an old man, Lane. Although, to be fair, 10 years ago, I was the age of many of you. Actually, 10 years ago, I was older than many of you, probably. Okay, so type that into your calculator using the common log. What is the common log of 500? 2.698. Well, 2.6990 approximately. So the difference in magnitude was 2.699, about 2.7. So maybe one of these earthquakes was like 5, one of these earthquakes was 7.7 or something. Who knows? I'm 29, but close, Bella. This is the difference of magnitude between those two earthquakes. This second earthquake was 500 times as much energy, but the magnitude of the earthquakes was only different by about 2.7. And that's the relationship between what does it mean to say an earthquake is magnitude 5? Has an exponential amount of energy. Okay. Anyway, well, yeah, but Vector is the only the bad guy from the first movie, right? Or is he in all of them? I didn't watch the second and the third. I heard they were less than stellar. All right. We did a section and a half today. Okay. I can't not stress enough how important it is to be good with this section. This is probably one of the biggest sections, along with function transformations, for the whole class. So even if you don't have to do this homework assignment, this 6.3 homework assignment, I would recommend doing it anyway. 6.3 is still going to be due on Tuesday though, because I already wrote your quiz for tomorrow and I don't want to write it again. So your quiz tomorrow will only be on 6.2, graphs of exponentials. Okay. But so this is the end of class. Feel free to head out. We're done talking about math. But hold up, Lexi. You thought the second and the third Despicable... Man, do you also think like Pirates of the Caribbean 8 was a good movie? I don't know if there's 8 of them, but there's too many, right? I don't know if I really trust your movie source. I don't know if I would use you as a reliable movie critic, Lexi. Lane thinks all the Pirates of the Caribbean movies are good? Okay. I'm not a big movie person, though, to be honest. I can enjoy a movie, but really, like, I don't even know the last movie I watched. I don't really watch a lot of movies except with other people. My favorite movie? I don't know. I don't think I have a favorite movie. I don't really have favorites of a lot of things. Except students. No, just kidding. I don't think I have a favorite movie. I don't have movies that I watch multiple times, really. There are movies I like and movies I don't like. But I can't even think of movies I like because I don't know. Yeah, you used to be the favorite student, and then you said you liked hard cookies, and just lost it. Minus 10 points. How dare you like something that I do not like? Actually, I like hard cookies too, just not as much as soft cookies. If you have cookies that are too hard, you just stick them in the microwave for like 5 or 10 seconds. It softens them up usually real good. And then they're warm too. Because warm cookies are way better than cold cookies too. Not too warm though. Anyway, I think that's probably about it for me. Have a great day, everyone.